Hi everyone, thanks for having me today. My name is Emma Marshall, and today, is this okay? I'm going to be talking about an idea that Deepak, Scott, and I started discussing this winter, and then so we've done some kind of preliminary work on this, and then we're really excited to bring it to SciPy to hopefully broaden this out into much more of a community discussion and effort. Many people might be familiar with the tidy framework for tabular data in the R language. What we're talking about today is what tidy data could look like for array data using Xray objects. First, a little bit about us. I'm a graduate student studying glaciology at the University of Utah. Scott is a geophysicist at the University of Washington, and Deepak is an oceanographer at NCAR, and this is us with all of our pets. So a bit of a roadmap about what we'll talk about today. We'll go a bit more into the problem, which is that we see a lot of duplicated effort among users of geospatial raster datasets, specifically during the processes or the steps of preparing these datasets for analysis. So what do we hope to do about that? Borrowing from the tidy framework for tabular data in R, we're going to talk about what tidy principles for array data could look like with Xray objects. And we'll do that by walking through real-world examples of data and the processes of preparing them for analysis. Can everyone hear me okay? I'm not sure if I'm okay. Cool. So a couple things I wanted to note before I move on. You'll see that all of the examples that we talk about today are satellite remote sensing data sets. And this is largely because this is just where our experience lies. And as a starting point, this is what we're working with. But that is one of the main motivations of having this conversation here, is to draw on all of the experience in the room and users in different domains. So we really hope to kind of generalize what we're talking about today, but this is where we are right now as a starting point. And then similarly, while we've done a lot of brainstorming about what these tidy principles and a tidy framework could look like built on Xray objects, we have by no means arrived at a definition of tidy data for array data. So we really hope that this is just the starting point and a community effort and a community conversation. So we would really love to hear from people after this. Really briefly, what is Xray? Xray is an open source project and Python package that provides labeled data structures for gridded array data. This is an image on the right here of a real world data set. This one is nicely organized, and you can see it's essentially an in-memory representation of a netcdf file. We'll see in the examples coming up that they don't always look like this, and they're not always as kind of like easy to work with as this object is. And then returning to the motivation for this, geospatial datasets are large, complex, and they can be cumbersome to work with. And the main motivation for this project came out of conversations at conferences like AGU and in Pangeo community meetings, and in experiences and discussions that we've had kind of along the way, that the hardest part of learning and teaching Xray is really helping students conceptualize and learning users conceptualize how to use the Xray data structure with their data. And what we think this comes down to is really specific understandings of the building blocks of these Xray objects. So those are data variables, dimensions, coordinates, and attributes, and how they all interrelate together, and how you can coerce your data into them so that your analysis is smooth and efficient. Where we specifically see this framework being useful is in kind of the point of a pipeline where the user has accessed data from an archive, and for very good reason, that data is often separated into temporal observations and spatial subsets. But most of the workflows that we're all performing want to use some sort of logical cube, right, and do investigation of some observable along spatial and temporal dimensions. And so that means that nearly every user is probably performing their own processes to assemble these logical cubes out of spatial and temporal subsets. So at a minimum, this is a lot of duplicated effort among many users, and I think it poses the risk of also, so essentially if we have this where we start, which is how we're accessing the data, and where we'd like to be, which is analysis-ready, workable data, that introduces a lot of decision points along the way, and especially for learning users, that those can be a lot of opportunities for missteps, hang-ups, and sources of confusion. And this is where we see all of the community knowledge of people have years of doing these things and creating their own solutions for this. This is an opportunity to harness those individual experiences towards some type of community framework that could provide a common expectation of what tidy, analysis-ready data looks like in this context, and patterns and tips on how to get there. So just quickly defining tidy data, it was developed by Hadley Wickham in 2014 for tabular datasets in R, and he wrote that it came out of his own experience organizing data for analysis and that of his students. He calls data tidying the structuring of datasets to facilitate analysis, and he writes that tidy datasets are all alike, but every messy dataset is messy in its own way. Tidy datasets provide a standardized way to link the structure of a dataset or its physical layout to its semantics or its meaning, and that's something that we'll return to in these examples. For tabular data, there are three main principles of what a tidy dataset looks like, and those are that each variable forms a column, each observation forms a row, and each type of observational unit forms a table. So now what we'd really like to do is imagine what that could look like for array data, and currently specifically in a geospatial context. So now we're going to walk through some examples of tidying real-world data sets, and our guiding question as we do that is going to be how could subsequent analysis with this data be made easier? So returning to those tidy principles for tabular data, we'll kind of try to orient them in the context of array data so they can kind of help us through these steps. And then we're going to think about the building blocks of an xray data set, which again are variables, and these should be the physical observables needed for your analysis. Dimensions, which are the axes defining the domain of the observable, coordinates, which are metadata that vary along a dimension, and attributes. These are metadata that is static. Metadata attributes should be added such that the dataset is self-describing, and this is inherited from CF conventions. So now we're going to look at some examples. The first example that we are going to look at is going to be constructing that analysis-ready XY time cube. And then after that, we will look at examples of, these are kind of newer data sets that are in cloud-optimized formats, and in some ways they come to us already analysis-ready or very easily coerced into that XY time cube, but then we will look at kind of the additional decisions that need to be made to really prepare that data set for analysis and access all of the information that it contains. So this first data set that we're going to look at is a data set of INSAR ice velocity over Antarctica. And remembering that guiding question of how could the analysis be made easier, we'll clarify that a little bit to think about what we want, which is an XY time cube with georeferenced X and Y coordinates. But now looking at what we have, so we see this data, so on the right here is the full data set, and it's just a lot of variables. So this is a zoom in of kind of the important things in the center here. And you can see that we have 2 dimensions, ny and nx, we have no coordinates, and then we have 32 data variables. But when we look at it, we can actually see that, which is more than we expect, right? We're not looking for 32 observables here. But when we look at it, we can see that we have Vx, Vy, and an error variable for each year contained in the data set. So we essentially have a time dimension embedded into our variables here that is going to make working with this data set more complex. In addition, we have these 2 variables at the end, which are x-axis and y-axis. These don't seem like they belong there. They are actually just providing us information about those observables, and they would be more appropriately stored as coordinates. So what do we need to do? We need to add a time dimension, add coordinate variables, and remove the time dimension from the data variable names. And once we do that, we arrive at this tidied object. You can see that this is much more intuitive to work with, and it lets us actually take advantage of the Xray functionality and to leverage all of those tools in our analysis that wouldn't be as accessible to the data in this format. This is just an example of what we can do once it's in this tidied format. Then we can just with one line really easily use Xray selection tools and then also visualization to take a look at our data. And so just like a brief note before we move into the next set of examples is that I think these are kind of like in some ways they're self-evident, right? Like we all do these in some ways, but each, like Hadley Wickham said, every messy data set is messy in its own way. And so these are going to be kind of like largely similar, but then tweaked processes that we're all writing for data sets. And I think it's really exciting to think about how we can kind of identify some common themes and principles and patterns out of them. So now we'll look at 2 examples of satellite imagery. These are intersensor or multi-sensor time sets of satellite imagery. The first is the harmonized Landsat Sentinel dataset. So this is Landsat imagery and Sentinel-2 imagery. And you can see that when we read this in using just Xray open dataset, we don't have a tidy object. And let's look at how this isn't tidy, right? So we read this in and we have a 3-dimensional object we could easily squeeze it into a two-dimensional object, but we really don't have much information from looking at the structure of that data set about its meaning. And its meaning is that these are reflectance values from a certain point in time and in space, which we have the spatial information, and then it's also a certain wavelength, excuse me. So we don't have any of that information contained in the data set. We're going to need to go to the file name for that. And as we're trying to scale up a workflow, that's going to be tedious and inefficient and cumbersome, and also for learning users, I think creates some examples or some opportunities to kind of get hung up and create mistakes. But luckily, this data set has metadata that adheres to stack specifications, and so we can use stack tools or tools built to inject stack formatted objects that are going to do a lot of the tidying for us. So once we format this with Open Data Cube stack, we can read these in as currently, so it's separated into Landsat observations and Sentinel observations, and then you can see that we have a nice XY time cube for each of those. But we still have a couple remaining issues. We can't just merge these together and have a workable object where we can actually leverage observations from both of these satellites. There are a couple issues, one being that we have different band naming schemes between the two data sets that we're gonna need to address before we can use these data sets in tandem. I'm not gonna talk about that today because I think like the more interesting example here is this data quality mask, which is the Fmask variable that you can see in both of these. And this is a mask to identify pixels that are affected by clouds, water, and snow. But what we'll see is that this mask is bit packed. And so it's quite a pain to like extract the information from this and actually utilize all of the information that is contained in this data set. So this is an example of what one might do to extract the bit-packed information in its current form to ultimately arrive at Boolean masks for each of those data quality types. You can see that it includes writing this extract function and then a ufunc, which is cumbersome, and it's more advanced code than we are like hoping your average user who's engaging with this data set should have to do just to engage with the information it contains. This is like, it works well, but it's a kind of a high bar to clear to just begin interacting with all of the information in this data set. This is an example of if the flag metadata were formatted in a way that adhered to CF conventions, then you can use another tool that is out there, which is CFXray, to ingest those flags and then return a Boolean mask to you. So this is an example of formatting, like using the tools and the formatting that are out there to create a much tidier data set or a much more easily tidied data set. Next, we're going to look at the ItsLive data set. This is a data set of ice velocity observations that are generated from satellite image pairs, and it includes Landsat 7, 8, and 9 imagery, as well as Sentinel 1 and 2 imagery. So we have a combination of optical and synthetic aperture radar imagery here. This data set is stored as Xarray data cubes in S3 buckets, and you can see that we read it in, and it is already in this really nice workable data cube. In a lot of ways, this is a really tidy data set, and we like the format of this a lot, right? Like, you can read this in quite easily, and then you can start figuring out what's going on with this data set, but it doesn't require a lot of kind of like advanced or even intermediate like Xray manipulation to get it into this format that then you can explore. But when we do take a look at it, we see that so we have XY time, coordinates and dimensions, and then we have 54 data variables, which is again a lot more than what we would expect with the observables that we're thinking about for this data set. So we can start to think about the ways that different variables are observables that we're interested in, and other variables provide information about those observables, and so the structure of this data set ideally should reflect that. This is an instance where CF conventions for ancillary data and coordinate types could really come into play with how the data is formatted and stored. And it's going to make the user experience much more smooth and intuitive, I think, once it's at that point. Another thing to note just about this data set is that this is an image pair data set, and the temporal separation of the image pairs is fundamental to the observable, which is different components of velocity. And right now, we have data variables indicating the acquisition dates, and then we index those off of the mid date. So this is kind of an instance where the structure of this data set doesn't really reflect its physical meaning, but that is something that currently in Xray, an interval type structure isn't supported. And so that's a way where I think like within the current capabilities of Xray, this data set is about as close in its physical structure to its actual meaning, but there is kind of additional work that needs to be done to appropriately take advantage of the information that this contains. So this brings me to some key takeaways. Important data stored in a file name is not the best thing ever. I'm sure we've all written a lot of functions to try to extract really important information from like a file name or a PDF file and things like that. And especially when you're scaling things up, that's not fun. Descriptive variable name, non-descriptive variable names, excuse me, can create confusion, as can missing coordinate information. And then the shape and structure of a data set, oftentimes or sometimes it can be embedded in things like variable names in a way that you might be trying to kind of like coerce a structure or a meaning that isn't in your structure through something that you have some flexibility with, like a variable name. But this is like a really good opportunity to stop yourself and say, hey, should I be doing this? That I think for a learning user, having that spelled out as kind of a framework could be really helpful. Some variables contain data about your observable, and some provide context about that observable, and so separating those into different data types and actually fully taking advantage of Xray structures or Xray objects like data variables and coordinate variables is very helpful. And then structuring data so that it adheres to common specifications really lets us work with the existing tools that are out there and makes the task of tidying much more simple, which I think as we're increasingly working with these cloud-optimized, very large and very complex and like multi-sensor data sets like this becomes increasingly important. So this brings us to some principles. So we've gone through these examples, right? And taking away kind of some of the key points of each of those brings us to these like summarizing principles. And this is kind of a starting point. This is a place where we would really love feedback from other users. I'm sure there's like many different, like these aren't going to work for every data set out there, but it might be a starting point that then you can kind of interrogate from there if it fits your use case or not, and then they can be adjusted and expanded upon. And then, so in conclusion, as we were thinking about these principles, what it really started to kind of come to in our minds is that this is like a pretty interesting conversation between dataset producers and dataset consumers. And these are groups that interact a lot, and sometimes an individual or a group might be kind of in both parties depending on the specific situation. But we kind of see this as a situation where dataset developers and users often have different needs or priorities, in that the developers would like to provide a large amount of information with minimal storage. Users would like easy access to that information, and those goals are oftentimes going to be at odds with one another. And I think this creates an opportunity to think about what could we kind of create as a community, what kind of framework could we have that can minimize the gap between those groups, and what could that look like, and what should that look like? I think this brings us to the tools ecosystem that I mentioned in some of those examples that are already kind of addressing a lot of those gaps and kind of trying to come up with a unified framework of how they are, could, and should be used in tandem with one another. And then that kind of brings me to where we go from here. As I said, this is very much an evolving conversation, and we'd really like to solicit perspectives from users of other libraries and in other domain areas. And then we're very open to like what this could look like. Is this a resource that is out there that is kind of a catalog of different tidying examples, and you could find a data set that matches the one that you have and then see maybe some suggested tidying steps? Is there a very generalized like skeleton tidy framework and then more domain specific, richer tidy frameworks that people can use? And then kind of the development of tidy tools on top of them. So I hope that this kind of maybe like you related to some of the steps that are in here or your students have, and everyone's, if thinking about ways that this could kind of play in the future in a way that we can kind of leverage a lot of this individual experience toward community knowledge that might make user experiences in the future a bit smoother. Thanks, and I'm happy to take any questions.
Thank you, Emma. Does anyone have any questions? Yeah.
It's more of a comment, I guess, but that was really cool to see all these tools that kind of work together to help tidy up the data that's not so tidy. You guys know about Kerchunk, I think, too, right? And so Kerchunk is kind of another way. I just wanted to let the audience know too that another way to sort of tidy up the data is to make those changes to tidy it up at the metadata level, and so then somebody has to do it only once, and then so you can make any collection of weird, very untidy data be tidy, in that way, and then but that works, if somebody does it for the community. But if they don't do it, then you need these other tools and stuff. So I love the idea of tidying up the data, though. It's awesome.
Thanks. Yeah, I think that speaks to kind of the necessity of the tools that we're talking about. So thanks for adding that.
Sorry, just to add on to that, like Stack, which was one that you mentioned, also, I think that's another benefit of that as well, that it operates like the data provider. I think you said this. The data provider doesn't have to necessarily do anything. Someone else can come along and provide that metadata. So I think that idea of using external metadata, either Kerchunked or Stack, it might seem weird because then the metadata doesn't live exactly with the data, but it can actually allow other people to come in and help with this process.
Mm-hmm. Definitely. Thanks.
I know you said you've just thought about this from the satellite perspective, but well, have you thought about it from the modeling perspective? I'm trying to apply it now, and I'm sort of thinking, oh, it already is kind of tidy, but I'm sure it's not. Certain aspects that you touched on for satellite data, you wouldn't necessarily have to deal with, but have you gone in that direction at all for thinking about ocean model output or atmospheric model output and what could be done to make it more tidy?
Yeah, so we've had conversations with people who are, I think, more actively in that area, and the common tidying things that they're finding and how translatable one is from one is to the next. So we've kind of begun to, but it hasn't crystallized into anything solid yet.
See if there are any other hands, but so is tidy data, does it go beyond CF compliant data? I understand coming from tabular data, the tidy concept, but coming to gridded data, we've always been make everything CF compliant and then you're good. Is tidy beyond that, or is it another way of sort of expressing that?
I think I would maybe ask Deepak what he thinks about that, because I think my understanding is that it could be somewhat case dependent and evolving, right? But depending on which data set you're working with, I think we're kind of acknowledging that how different information that comes up in a workflow, just having guidelines of how it can be stored, and some of those might be CF, ancillary variables and things like that. But I think it might be a bit more of a prescribed way of dealing with it at each step of a workflow. But I'd see if.
I think you said that very well. I think there's a lot of overlap, and particularly when it comes to stacking is maybe where the conventions don't help you so much, and it's more about Stack or Kerchunk or catalog. But I think in general, it seems like there's a lot of overlap from what, at least the examples we've looked at. And if someone's got another example, that would be great to see.
I'm curious if you've thought about if and where you might want this conversation to continue, and kind of how you might get broader input from, because I'm sure there's a lot of great perspective in this room, but there's a lot more of it outside of this room.
Yeah, absolutely. Thanks. Oh, and I should put up here maybe. So we have a repo started for this, and right now it's kind of a place where there's a little bit of notes and then some examples, and there's a Jupyter book based on that as well. So I think that would be a great place for some for contributions to be. But then also I think we've shared a document in some Pangeo community meetings, and really like those, I would love to continue having those types of conversations in that context or outside of it, if there were enough interest to kind of like schedule a meeting after this, or to solicit thoughts, questions, feedback, comments in a GitHub repo. Thanks.
Any last questions? All right, let's thank Emma one more time.